Hello and welcome to this practical session. In the previous session, we did an experiment on a free vibration response of a trifilar pendulum and a simple vibratory system. In today's session, we are going to look at coupled pitching and bouncing motion, and for that we have a small experimental test setup in the lab here, which is essentially a small plate, and on that we have an electric motor mounted in the center. The motor is going to rotate, and the rotation is going to excite this plate, which is supported on these two springs at the ends, and the vibration is because of the harmonic excitation generated because of the rotation of the motor shaft. And to generate that harmonic excitation, we have two discs mounted at the ends of the shaft. So these discs have unbalanced masses which are placed at these two disc surfaces. So the motor has these two discs mounted at the ends of its shaft. The discs have unbalanced masses placed, and these unbalanced masses excite the plate into vibration because of the centrifugal force, which is going to change its orientation as the discs rotate along with the motor shaft. Now we have an arrangement here with which we can place these two unbalanced masses in phase, so that the net excitation force is acting in the same direction in both the discs, or we can place them in opposite phase. So in the sense that this mass on the disc, on the right disc, and the mass on the left disc, they can be put in opposite phase, so that the net effect of the rotating unbalance is to create an unbalanced moment rather than an unbalanced net vertical force. Okay, so depending upon whether these two masses are in phase or they are in out of phase, you may generate a harmonic vertical force, okay, or it can generate a moment, okay, about this axis of the motor. So why are we doing this? Because this motor mounted on the plate is an inertia here, and the plate is supported by these two springs. So in a sense, what we have here is a system that represents, let's say, a car body, which we discussed in the lectures, that it can have a bounce motion depending upon how the force is acting on the plate, and it can also have a pitch motion if there is an excitation moment that the rotation of the motor will create. So we are going to look at the conditions wherein we get a pure pitch mode of vibration. So to start with, if you remember, we discussed a condition wherein there is a decoupling of the pitch motion and the bounce motion, in which the stiffness of this particular spring multiplied by its distance from the center of the position of the center of mass of this entire system, if that product is equal to the stiffness into the distance between the center of mass and this spring position, if these two products are equal, then this is going to decouple the two modes or the two motions. That means the bouncing will be pure bounce motion and the pitching will be pure pitch motion. Now for that purpose, these two springs that we have supported, these two springs which we have supporting the plate, these two springs are of equal stiffnesses, and therefore if we place the motor in the center of the span between the two springs, then we will have the condition of decoupling of the two modes. So by locating this motor in the center of the span, we are likely to get a pure bounce mode and pure pitch mode. Now you will get a pure bounce mode if the excitation force excites the system in the vertical motion, and you will get a pure pitch mode if the two unbalanced masses are put in out of phase, so that the excitation is through a moment generated about the axis of the motor or about the CG. And that is what we are going to observe here. Theoretically, we know that when the masses are in phase, we expect to get a pure bounce mode and not pure pitch mode, because even if the pure pitch motion exists for this particular vibratory system, you need to have an appropriate forcing to excite that motion. But in this case, when the masses are in phase and the unbalanced force is the net unbalanced vertical force, there is no moment which is generated if the forces are in phase at these two disk locations, and therefore, we will not have any excitation to excite a pitch motion of this system. Now, for doing that, what we have is this motor is operated by a controller here, a rheostat, which will help us to change the operating speed of the motor, and therefore, the excitation frequency to this vibratory system can be modified or can be changed. So, we are going to sweep from 0 RPM onwards and check at what speed we get resonant vibrations, and that resonant vibrations would indicate that the speed of rotation of this motor is matching with the natural frequency of this particular system. Now, when the system has decoupled motions of pitch and bounce, then the uncoupled pure bounce mode natural frequency and uncoupled pure pitch mode natural frequency are the two natural frequencies that we expect. Now, we are going to verify that with this theoretical condition of the center of mass being exactly in the center of the span between the two spring supports will generate pure bounce or pure pitch. So, I am going to now start spinning this motor and look at what speed we get pure bounce motion. Now, you can see that the plate is beginning to vibrate, and then let us cruise this the motor to a speed wherein a large resonant vibrations are observed. So, I am going to use a tacho to find what is the speed at which this is rotating at the moment. So, at roughly about 490 or maybe 500 here, as I can see the tacho giving me the reading of about 480 or so, 490, and sometimes it touches 500 RPM, and when it does that, I can observe a large bounce mode motion. Yeah, you can see now that this whole plate is bouncing up and down, and that speed is roughly 500 RPM. It fluctuates because the motor is hard to maintain its speed, but you can now see that the whole plate is bouncing. Okay, the kind of motion that you observe is that the whole plate is just bouncing with large amplitudes, and so this is the bounce mode. Now, prior to reaching this bounce mode or slightly at a higher speed, we did observe. Yeah, so you can see that this is very clearly a bounce, pure bounce mode, and there is hardly any pitching that you observe here. Okay. Yeah, so roughly 500 RPM is what my tacho is showing here, and that is the speed at which you are getting a large amplitude of vibration in the bounce mode. You can notice that there is no pitch motion here, the entire plate simply vibrates up and down, and hardly any pitch motion is noticed. Yeah, roughly 505 or 500 is the speed which we are observing here. If I increase the speed, you can see that quickly the vibrations have dropped a lot significantly, and sometimes you might observe a motion which you might say is a pitch motion, but it is actually not a pitch motion. It is the motion in this plane that you observe, okay, and that is in the horizontal plane, which in our numerical model we did not consider. Yeah, you can see that this kind of a motion, that is the yaw motion, that is also observed, obviously because the unbalance is going to excite the horizontal, generate the horizontal excitation force, and that might excite the plate to vibrate laterally, and because the springs do provide some resistance in the horizontal plane motion. So, you may have additional resonance in the horizontal plane, but in our theoretical model we always consider that the vibrations are in the vertical plane, and then that kind of a mode we try to match. So, what I am going to do now is change the phase of these masses and see whether I can detect a pitch mode of vibration. But in the existing condition of these two masses which are in phase, we really did not observe any pitch vibration. Okay. So, we can see that in the entire speed range we hardly had any pitch motion. Okay. The motion that we observed was in the yaw and predominantly the bounce mode. Okay. Now, what we have done is we have changed the unbalance mass orientation. That means, the unbalance in this disc is at 0 position, and in the same reference this unbalance on the second disc is now exactly out of phase. That means, this is 180 degrees with respect to the unbalance orientation in the left hand side disc. So, now what is going to happen, that if this shaft rotates, the unbalance force in this disc and the unbalance force in this disc, they are in opposite direction, and they will create a pure moment, okay, without generating any net vertical excitation force. So, the force is 0 and there is going to be moment, and that is essentially required to excite the pitch mode or pitch motion of this particular plate. And so, what we do now is scan again the entire speed range starting from 0, and in the previous setting where we had the two unbalanced masses in phase, it generated an excitation force, and that excited the bounce motion. Now, we shall check whether that bounce motion still is observed given the kind of excitation condition we have here, and then look at the pure pitch motion, okay, or the mode in which there is only pure pitching motion taking place of this vibratory system. Now, that is what we are supposed to do now. So, I am going to start the motor and take the speed from 0 onwards and scan through the entire speed range. So, this is another way of finding out the natural frequency of the system by observing resonance phenomena rather than counting number of cycles and the time associated with it. So, here the speed currently is about 400, about 450 or so, and the speed at which we had observed a pure bounce mode resonance, that is not seen now because the excitation is different in this case. There is no bounce motion observed when I am scanning past the bounce mode natural frequency. So, I am going to now take it past, and now what we are observing is a pitch mode. Okay. So, the pitch mode motion or the resonance corresponding to pure pitch natural frequency is being observed here, and the speed that I am getting this is roughly 950 or so. I am trying to locate that precisely by changing the speed, and now you can see that this motion is a pitch motion. This part is going up, this is going down, and when this is happening, there is no vertical motion of the whole plate, and that's precisely what the pitch mode motion that we know of. Okay. The speed that I am observing here on the tacho is about 980 rpm. We can fine tune it so that we get little more larger level of pitch vibrations. So, it is definitely more than 900, because when I dropped it below 900, the amplitude drops significantly. Yeah, you can see that this is the pure pitch mode vibration happening roughly around 980 or so. Yeah, you can see that this is very violent pitch mode vibrations, and when I took it past 1000 rpm, the vibrations suddenly dropped. You can see now these vibrations are almost gone when I took it beyond 1100 rpm, but somewhere here you can observe the vibrations are very violent. So, now what we have learned, that it's not that when the system has two natural frequencies, we will observe the two resonances. The system does have these two natural frequencies, but which one will get excited depends upon the excitation function or the way we are exciting it. For example, the system had two distinct natural frequencies, the decoupled bounce mode natural frequency and the decoupled pitch mode natural frequency. But depending upon how we excited it, in the first case, when the unbalances were in phase, there was only vertical force motion, or excitation force was in the vertical plane, it was a force excitation, and in that case we did not observe the pitch motion resonance. Okay. So, the second natural frequency was not actually excited, whereas when we change the excitation in such a way that it generates a moment, in that case pure bounce mode was not excited, but pure pitch mode was excited, and so we observe the second natural frequency or the resonance corresponding to second natural frequency. Although that does not mean that the system has only one resonance, it does have two natural frequencies, there will be two resonances, but then we should have excitation given to the system in a way to excite that particular natural frequency or the motion corresponding to that natural frequency. Okay, so, having discussed this, what we discussed is that when the mass was in the center of the span, the springs are identical in their stiffnesses. So, we had two decoupled natural frequencies. Now, what we are going to do is to shift this mass slightly from the central position, and when we shift it, what happens is that there is going to be an unbalance in terms of the restoring forces generated at the two supports, and therefore, it is not possible for this particular system to vibrate in pure pitch or in pure bounce mode. So, the modes are now going to get coupled. So, when you shift the mass from the center of the span slightly away, you no more will get pure pitch mode natural frequency or pure bounce mode natural frequencies, but you will get two coupled pitch and bounce mode natural frequencies. Okay. So, that is what we are going to do by shifting the motor slightly away from the center of the span, and then observe what kind of a motion or what kind of a resonance and the corresponding motion you observe. Okay, now, what we have done? We have shifted the motor from the center of the span, shifted it slightly off the center, and when you do that, the spring stiffnesses being the same, we are now going to have a situation where K1 into L1 is not going to be equal to K2 into L2. That is the condition we discussed in the lectures, and that condition being not satisfied, we cannot have this entire system executing pure pitch or a pure bounce motion. And the resonance that now we are going to observe are expected to be, coupled pitch and bounce motion resonance. And so let's look at the two frequencies that we now get. Okay. So, I am going to run the motor again and check what are the speeds at which we get the two new resonances. So, you can see that the speed currently is about 270 to 90. So, you can see that there are vibrations and resonance conditions which we observe now. Yeah, you can see this. This is observed at here. About 1000 hertz, 1000 RPM.